We're going to look at a few techniques that will help us to simplify integrands, the functions inside of an integral or antiderivative, in order to be able to solve problems we might not otherwise be able to. We'll look at a few examples for each of these. Those techniques include the familiar substitution, multiplication by 1, dividing polynomials, separating fractions, and completing the square. When we use substitution, we generally have some function capital F of x, which is an antiderivative of little f of x, which means that capital F prime of x is equal to f of x. The chain rule then tells us that the derivative of capital F of g of x is equal to capital F prime of g of x times g prime of x, which we can then rewrite as little f of g of x times g prime of x. Taking the antiderivative of both sides of that expression, we see that the antiderivative of little f of g of x times g prime of x dx is equal to big F of g of x. We can then perform the actual substitution. We can let u stand in for g of x, which means that du stands in for g prime of x, giving us the formula the antiderivative of f of u du is equal to capital F of u. In practice, when we're working a substitution problem, we're looking for a function g of x somewhere in the integrand whose derivative g prime of x also appears in the integrand in order to make our substitution. Let's take a look at this in an example. We have the antiderivative of tangent of x dx. This has no known antiderivative, so what we're going to do is rewrite tangent of x as sine of x over cosine of x. So now we have the antiderivative of sine of x over cosine of x. Here we can see that we have a function whose derivative is also inside of the integrand. That function is cosine x. So we're going to let u be cosine x. We'll take the derivative of that. We get du is negative sine x dx. If we divide both sides of that by -1, we get negative du is equal to sine x dx. We can now make our substitutions. We're going to replace cosine x with the thing that it's equal to, which is u. We'll replace sine x dx with the thing that it's equal to, which is negative du. So our original antiderivative is now equal to the antiderivative of negative du over u, which we know we can move the negative to the outside, and the antiderivative of du over u is the natural log of the absolute value of u plus a constant c. Since we started off with a function of x and we're taking an antiderivative, we want to end up with a function of x, so we replace u and we get that the antiderivative of the tangent of x dx is equal to the negative natural log of the absolute value of the cosine of x plus a constant. Let's take a look at another example, the antiderivative of x times e raised to the x squared power dx. So we're looking for a function whose derivative is also in here. We notice that the derivative of x squared is a multiple of x, so we can make that work. We're going to let u be x squared. That means that du is going to be 2x dx. We can divide both sides by 2 to get 1/2 of du is equal to x dx. Now we'll make our substitution. The x dx is going to get replaced by 1/2 du, and the x squared will get replaced by u. So our integrand now is we have the antiderivative of e raised to the u power times 1/2 du. We can move the constant out front to get 1/2 times the antiderivative of e to the u du, which is 1/2 of e to the u plus c. Once again, we want to replace u with its corresponding value, and we see that our final answer is 1/2 of e raised to the x squared plus c. Let's take a look at one more example. Here we have a definite integral from 0 to 2 of 4x over x squared plus 1. We're going to do the same thing. We're going to look for a function in here whose derivative or a multiple of the derivative also appears. We can see that the derivative of x squared plus 1 sits inside of there if we manipulate it a little bit. So we'll let u be x squared plus 1. So that du is then 2x dx. We need 4x dx. So if we multiply both sides by 2, we get that 2 du is 4x dx. We're going to replace the 4x dx with 2 du. We'll replace the x squared plus 1 with a u. Rewriting the integrand, we now have 2 du over u. However, we have to make a substitution for the limits of integration as well. Those are originally belonging to x. So the original integral was x equals 0 to x equals 2. When x is 0, because u is x squared plus 1, we know that u must be 0 squared plus 1, which is 1. Similarly, when x is 2, u is going to be 2 squared plus 1, which is 5. So our new limits of integration are u equals 1 to u equals 5. We'll move our constant to the outside, so we have 2 times the integral from 1 to 5 of du over u, which we know is the natural log of the antiderivative of that is the natural log of the absolute value of u from 1 to 5. Because we made that switch, we do not rewrite u in terms of x. Our limits now specifically belong to u, so we end up with 2 times the natural log of 5 minus the natural log of 1. But we know the natural log of 1 is equal to 0, so we just get 2 times the natural log of 5. Our next technique is an algebraic one. We're going to use something called multiplication by 1. So our goal here is to simplify the integrand by multiplying by 1, but our challenge is going to be to find the exact right form of 1 to use to make our lives easier. Let's take a look at an example to see how this might work. Here we are looking for the antiderivative of 1 minus x all divided by 1 minus the square root of x dx. This doesn't fit any of the patterns that we've seen before. And there's nothing in there whose derivative it also appears in there, so substitution won't work. However, we've seen the idea of rationalizing the denominator before. Part of the issue we have with this integrand is that it has a square root in the bottom. So we're going to try that. Rationalizing the denominator involves multiplying by a version of 1 that allows us to get rid of the radicals in the denominator. So we're going to multiply the entire integrand by 1 plus root x over 1 plus root x. On the top, we're not going to multiply it out just yet. We'll see if we need to or not. On the bottom, when we distribute, we see we get 1 plus the square root of x minus the square root of x minus x, which is exactly what we hoped for, because that allows us to eliminate the square root of x on the bottom. And now we have 1 minus x times 1 plus root x all over 1 minus x dx. Handily, the 1 minus x's cancel each other out. So now we've simplified this integrand to be 1 plus the square root of x dx, which we know how to anti-differentiate. I'm going to rewrite square root of x as x to the 1/2 so we can apply our power rule easily. And we see that our antiderivative here is going to be x plus 2/3 of x to the 3/2 plus some constant c. Let's take a look at another example. Here we have the integral of e to the 2x all over e to the 2x minus 4 e to the negative x dx. We can't rationalize the denominator because there's no radicals. We can't use the substitution because even though the derivative of e to the 2x does appear in there in some form, we have this negative 4 e to the negative x floating around. But if we multiply the top and the bottom by e to the x over e to the x, we can get rid of that e to the negative x. When we do that, we get e to the 3x on the top, and then we get e to the 3x minus 4 e to the 0 on the bottom. But e to the 0 is equal to the 1, so the denominator becomes e to the 3x minus 4. Now we can use substitution. We notice that the derivative of e to the 3x minus 4 looks a lot like e to the 3x. So we'll let u be e to the 3x minus 4. du is then 3e to the 3x by the chain rule, dx. So if we divide by 3, we get 1/3 of du is equal to e to the 3x dx. Now we'll make our substitutions. We can bring the 1/3 out front, so we have 1/3 times the integral of du over u, which we know is the antiderivative of that is the natural log of the absolute value of u. So we get 1/3 times the natural log of the absolute value of e to the 3x minus 4 plus a constant c. Our next technique is going to involve rational functions. We're going to try to divide polynomials, and we'll simplify our integrand by using long division. Let's take a look at an example. Here we have a 5th degree polynomial in the numerator, a 2nd degree polynomial in the denominator. Nowhere in there do we have an obvious place to make a substitution, so we're going to try to simplify things a little. We'll go ahead with a long division. So we've rewritten the denominator on the outside, x squared plus x plus 1, and we're dividing that into negative x to the 5th minus x to the 4th minus 2x cubed. We'll hold the place of the missing x squared plus 4x plus 3. Dividing negative x to the 5th by x squared gives us negative x cubed. Then we proceed with the division algorithm. We multiply and we subtract everything, which is just going to change our signs. When we do that, we see that the x to the 5th terms cancel each other out, the x to the 4th terms cancel each other out, and we're left with a negative x cubed. Then we bring down the 0x squared plus 4x plus 3. And we'll divide again. Negative x cubed by x squared gives us negative x. Multiplying again, we have negative x cubed minus x squared minus x. Subtracting everything, we'll add and change our signs. That's going to give us x squared plus 5x plus 3. We can do one more division. X squared divided by x squared is 1. Multiplying that out, we just get x squared plus x plus 1, which we're going to subtract, so we'll change all of our signs. And we end up with 4x plus 2. So now we can rewrite our integrand. We're going to use the quotient we just got. We get negative x cubed minus x plus 1 plus our remainder 4x plus 2 over our divisor, x squared plus x plus 1 dx. The first half of that's fairly easy to integrate. So we'll rewrite this as the antiderivative of negative x cubed minus x plus 1 dx plus the antiderivative of 4x plus 2 over x squared plus x plus 1 dx. If we look at that second part, we're going to need a substitution, noticing that the denominator, its derivative appears in the numerator. So we'll let u be the denominator. Du then is 2x plus 1. Multiplying by 2, we get 2 du is 4x plus 2 dx. Now we take the antiderivative of the first part. We get negative 1/4 x to the 4th minus 1/2 x squared plus x. We're not going to worry about c just yet. We're going to add to that 2 times the integral of du over u. Rewriting the first part, negative 1/4 x to the 4th minus 1/2 x squared plus x. And then we get 2 times the natural log of the absolute value of u plus c. We only need one c. And now, of course, we'll replace u by what it was equal to in terms of x. So our final answer is negative 1/4 x to the 4th minus 1/2 x squared plus x plus 2 times the natural log of the absolute value of x squared plus x plus 1 plus c. Our next technique is going to involve splitting up fractional integrands into multiple simpler integrands. So for an example of this, let's consider finding the antiderivative of sine x plus 1 over cosine x. Even though the derivative of cosine x appears in there, it has 1 added to it, so a substitution is not going to work for us. However, we can split this up. We can rewrite it as the antiderivative of sine x over cosine x plus 1 over cosine x dx. That can then be split into two integrals. The first is the antiderivative of tangent x dx. The second is the antiderivative of secant x dx. Tangent, we did earlier using substitution, so we know that that one is the negative natural log of the absolute value of cosine of x. Secant x, we're going to have to work a little bit harder to find the antiderivative of this one. It turns out that a trick of multiplying by 1 is going to be what does it for us. We know that secant squared of x is the derivative of tangent of x, and we know that secant x tangent of x is the derivative of secant of x. So what we're going to end up multiplying by is secant x plus tangent x over secant x plus tangent x dx. So that when we distribute our original secant x, we end up with those two functions that are known derivatives for us. And that's going to be useful for doing a substitution. So we multiply across and we end up with secant squared x plus secant x tangent of x all over secant of x plus tangent of x dx. Now we can do our substitution with u being the denominator of that expression. Then du becomes secant x tangent of x plus secant squared of x dx. We've now turned that antiderivative into the du over u. That gives us the natural log of the absolute value of u, which we know is the natural log of the absolute value of secant of x plus tangent of x. We'll add on our constant. Putting it all together, our final antiderivative for the original function is the negative natural log of the absolute value of cosine of x plus the natural log of the absolute value of secant x plus tangent of x plus a constant. We'll do a definite integral for our next example. So we're going to integrate between 0 and pi over 4. Our function looks like secant of theta plus cosecant of theta all over secant of theta times cosecant theta d theta. We're going to split that up. We'll split up our numerator, keep our denominator in both places. So we'll have the integral from 0 to pi over 4 of secant theta over secant theta cosecant theta plus cosecant theta over secant theta cosecant theta d theta. Still integrating from 0 to pi over 4. The first one, the secants cancel each other out, and we get 1 over cosecant theta d theta. In the second one, the cosecants cancel each other out, and we get 1 over secant theta d theta. We're still integrating from 0 to pi over 4. Our values haven't changed there. 1 over cosecant is the same as sine, so we have sine theta d theta, and 1 over secant theta is cosine. So we have cosine theta. Those are both known integrals for us. We know the antiderivative of each of those. So we get negative cosine of theta from 0 to pi over 4. And then we get positive sine of theta from 0 to pi over 4. Plugging in, we'll have negative cosine of pi over 4 minus a negative cosine of 0, which turns into plus cosine of 0. Plus sine of pi over 4 minus sine of 0. The cosine of pi over 4 is root 2 over 2, so we get negative root 2 over 2. The cosine of 0 is 1, so we get plus 1. The sine of pi over 4 is positive root 2 over 2, and the sine of 0 is 0. So altogether, we end up with 1. Our last technique involves rewriting quadratic functions in ways that we can turn them into recognizable integrands by completing the square. So for our example, we're going to find the antiderivative of 10 over x squared minus 4x plus 5. This is not a known antiderivative, and a substitution won't work, but we notice that we can rewrite the denominator as x squared minus 4x plus 4 plus 1. When we do that, now our integral looks like x minus 2 squared plus 1 with 10 in the numerator. We'll move the 10 outside. We get 10 times the antiderivative of dx over x minus 2 squared plus 1. That is a pattern that we have seen prior to this. So we'll do a quick substitution, letting u be x minus 2, which makes du equal to dx. We now see that this is 10 times the antiderivative of du over u squared plus 1, which we know is 10 times the inverse tangent of u plus c. Replacing u, we get the inverse tangent of x minus 2 plus c. We're going to put a few of these ideas together in our last completing the square example. So we'll do the definite integral from 0 to 2 of x over x squared plus 4x plus 8. And we'll notice that our denominator can be rewritten. So we have x squared plus 4x plus 4 plus 4 as our new denominator. The first three terms make a complete square. So we have the integral from 0 to 2 of x over x plus 2 squared plus 4 dx. We're going to let u be x plus 2 and du be dx. However, notice we have x dx in the top. So we're going to rewrite x as u minus 2 using the substitution that we made. Our original limits are x equals 0 and x equals 2. We're going to rewrite those as u equals 2 and u equals 4. So now our integral is the integral from 2 to 4 of u minus 2 over u squared plus 4 du. Now we're going to use our splitting technique. So we'll rewrite this as the integral from 2 to 4 of u over u squared plus 4 minus 2 times the integral from 2 to 4 of du over u squared plus 4. We'll take the first part of this separately. So that integral is going to be the integral from 2 to 4 of u over u squared plus 4 du, which we see that the derivative of the numerator or the denominator is in the numerator. So we'll let v be u squared plus 4 so that dv is going to be 2u du, which means that half of dv is equal to u du. We need once again to replace our limits of integration. So when u is 2, that means that v must be 8 because it's u squared plus 4. And when u is 4, v is 20. So that integral becomes the integral from 8 to 20. Move the 1/2 to the outside, we get dv over v. We know that that is 1/2 the natural log of the absolute value of v, evaluated from 8 to 20. Which is going to give us 1/2 the natural log of 20 minus the natural log of 8. Using laws of logs, we get 1/2 the natural log of 20 over 8, which simplifies to be 1/2 the natural log of 5 over 2. Now we'll look at the second half of our integral. We have negative 2 times the integral from 2 to 4 of du over u squared minus 4. This one falls into one of our patterns. This is an arctangent interval, so we get negative 2 times 1/2 the inverse tangent of u over 2, evaluated from 2 to 4. The negative 2 and the 1/2 are going to just make a negative 1, so we get negative 1 times the inverse tangent of 4 over 2, which is 2. The two negatives together make a positive, so we have the inverse tangent of 2 over 2, which is 1. The inverse tangent of 1 is pi over 4, so we get pi over 4 minus the inverse tangent of 2. Putting it all together now, the two antiderivatives or the two definite integrals we just computed, we get that our final answer is 1/2 the natural log of 5 halves plus pi over 4 minus the inverse tangent of 2.